Welcome to Xcoder videos and to the start of our HDL challenge. I want to welcome everyone for our live presentation this evening, and we're going to explain um, the work that we're going to be doing over the next several weeks, and I hope that it will be something that will be a real challenge to some of you and be an enjoyable way to spend some time over the next few days. This is called the HDL challenge because we're going to be employing HDL or hardware descriptive language to build the components that we're going to build. If you've been watching the videos the last several weeks where we were looking at the macro-hard program, then you know what we're doing here. If not, perhaps you need a little bit more explanation of what we're going to do. Basically, what we plan to do will be to give some specifications of hardware, logic gates like AND gates or OR gates, things that they make chips to do in logic circuits, and we're going to build those, at least in a simulated way. And this is all going to be done in software, of course, with programs and things of that nature. But if you like a challenge, if you like logic, this is really a very enjoyable thing to do. And we're going to be working with this program and some programs that will allow us to do some testing and things of that nature. This program that we're going to be following is based upon building hack one chip at a time, based upon the NAND to Tetris course by Noam Neeson and Shimon Shokin, which is available free of charge at Coursera.org if you want to audit the program, or you can pay them and take the test and take their the tests that they give with the class and get a certificate at the end showing that you've taken the class. And viewers can view these videos at Coursera.org either by paying for the course or auditing the course, as you can look at these videos that we're doing here as a supplement to that course, but it's not required that you take anything at Coursera if you're not inclined to do that. Let me go over some of the requirements, some of the things that you'll need in order to follow along with what we're doing. First of all, you'll need to download free software that goes along with the course, and that will also go along with these videos that we'll have over the next several weeks. And the software is called NAND to Tetris, and you can download it by going to www.nandtotetris.org/software. NAND is spelled N-A-N-D, the number 2, Tetris, like the game, TETRIS.org/software. And you need to precede that with an HTTPS so that you'll get the secure site. You'll want to extract the software. The software comes in a zip file, and extract the NAND to Tetris folder from within the disk file to your desktop or to some other convenient location on your computer where you'll remember it and you'll be able to get to it easily. If you don't already have it installed, most of you are going to have it already, but if you don't, you may need to download Java Runtime Environment from https://www.java.com/en/download. And if you go there, they'll have instructions for downloading and installing the Java Runtime Environment, and that's necessary to run the software from nandtotetris.org. And one other requirement that we have, and really it's the only reason for this these videos that we're doing, and that's just to have fun. Make sure that we're not going to do anything in the class that expects more from individuals than what they're able to do. And if you know what you're doing, you'll be able to do a whole lot. If you don't, you might have to struggle a little bit to get going, but that's okay. You can do whatever you want, whatever you can do in that regard. This is what the main folder looks like from NAND to Tetris. There are two directories under NAND to Tetris. One is a tools folder and the other is a bin folder. Right now you're looking at the tools folder. And I think in just a moment, I wonder if I've stopped that. I guess I did. There are a number of files within the tools folder, especially some batch files if you're running Windows. If you're running Mac or Linux, then there are some .sh files that you can use to kick off the GUI applications that are in that tools folder. There's also a folder called projects, and within the projects folder there are 14 additional folders numbered 0 to 13, and each of these folders has various files within them that will be used within the weekly tasks that we'll be doing. There are the main files in them are the .hdl files, and these are the HDL stubs for the various components that we're going to be building over the next several weeks. And those stub files provide the specifications for the chips and for the gates, and we'll be creating additional files for testing our designs. We'll be able to do that. The .hdl files are HDL stubs that describe the gate or chip and specify the interface that the gate should use. And our job will be to provide the parts and the connections that are needed to make the gate work. Note that the tools included with NAND to Tetris do not include an HDL editor. We're expected to use a text editor like Notepad or Notepad++. However, I am working on an editor that I hope to have ready to share by next week. And this editor will make it a little bit easier to create and edit these HDL files. The hardware simulator is going to be the main program that we're going to use during these next several weeks. And this is This program will allow us to load up these HDL files that we have created by adding in the parts and the logic to do the things that the various gates are supposed to do. And this program will take those HDL files and simulate the hardware so that we can see how it works, to see if it passes the tests that are made available in test files, and compare the results of our components with the expectations that have been set for each of these designs. And we can write our own scripts if we want to create additional gates, helper gates, that are not specified in the challenge, and we'll try to look at the scripts so that we can write our own scripts to run tests and to make tests work for each one of the gate files that we create, whether we're creating one of the specified gates or one of our own choosing. Now, for this first week, these are the gates that we're going to assign. And these will all be found within the project 1 folder. Let me show you what this is going to look like. I have on my desktop the NAND to Tetris folder, and within the NAND Tetris folder, I have the tools folder and the projects. If I go into the projects folder, here are the 14 folders that specify that contain the files that we're going to need. Now, you can ignore the 0 folder. This is the folder we're going to work on this week. And in this folder, you can see a number of files. We start off, I have sorted based upon type, so they start off with the CMP files, and these are files that have truth tables within them for each of the components that we're going to work with. This is the truth table for an AND gate. And you'll notice where A and B will be either a 0 or 1. The output for an AND gate looks just like that. And we have one of these CMP files for each of the logic gates that we're going to be creating. There's also these TST files. Let me open up the AND TST. This also is a text file, and the test file is fairly simple. It specifies that the simulator load up the and.hdl file, and it says to output the results of the test to and.out and compare and.out to and.cmp. That's the file we just looked at. And then the output to list, this is what's going to go into the output file, and that will be the A, B, the A input, the B input, and the output. And then for each of the tests, we have a section here where we set A to 0, set B to 0. Then evaluate just means to run the test, and then to create the output that will go into the AND CMP. And there's one of these for each, for this logic gate, there's one of these for each a combination of A and B, 0, 0, 0, 1, 1 and 0, and 1 and 1. And by running this, the and.out file will be created, and then the comparison will be made at the end, and that comparison will be given, the result of that comparison will be given in the hardware simulator. I'll show you how that works in just a few minutes. And finally, there are these HDL files. Here is the AND HDL file. I'll open it up. And we have the specification for the AND HDL files. And this specification has a header. This first section that starts with the double slash marks is called the header. It doesn't do anything with regard to the logic of the gate. Obviously, it's just information about what's in the file. And then we have this section. This is just a different kind of comment. However, the NAND-to-Tetris folks call this the API section, and that's what we're going to call it. And this is to describe how the gate is supposed to work. It's an AND gate, and if A and B, that is A and B are true, A is true and B is true, out will equal 1, otherwise out will equal 0. So it's going to be 1 only when A and B are set to 1, and every other case is going to output a 0. The chip then, this is the logic, the start of the logic for how the chip operates. And we start with the name of the chip, then the inputs. We have to name the inputs, and then the outputs are named. And in this case, there's just one output called out. And then finally, the parts section. This is to be replaced with the parts and the connections that are necessary to make this component do the work that it's supposed to do. And that's the hard part, and so that's the part that you get to do. All right? And this looks like a lot of gates, and probably will do more gates in this week than any other time, but these are the simple gates. Most of these are just going to use very few components, and they're easy to wire up. There may be a few of these that are a little more involved, but that really will keep it interested. And I'll talk about some other resources that are available for you and could add to your enjoyment. I've already mentioned the Coursera class. If you want to look at this class and consider taking it, you can follow the link that I have here for it. It's at www.coursera.org/learn/build-a-computer/home/info. And you can go and find out about that course there. The project page for the NAND-to-Tetris projects that we're going to do is at the www.nandtotetris.org. And project 1 is where you can go and get more information about these these gates that we're going to be creating this week. Every week we'll have one of these locations to go to, and we're just going to go to project 1 this time under the www.nandotetris.org website. And then also this digital logic simulator. We've talked about this before in previous videos. This will allow us to graphically create logic circuits and do some testing with them. I like doing that a little bit better than drawing them out on paper, and gives me a little bit of help. And that's available at github.com/HNeeman. That's spelled HNEEMANN/digital. At github.com/HNeeman/digital. And that's the digital logic simulator. Now, in the class, the instructors went over for this first week Boolean logic. And I'm just going to go over a little bit of the same material that they went over because that might help us in designing these gates that we're going to be working on this week and the gates that we'll work on in the future. Each one of the specifications is going to clearly describe the gate's functionality, and they're going to be precise about it. Maybe giving out a truth table, or at least in a way that you can write the truth table out for yourself. And these truth tables are really important. They can help us determine what to do in order to create these gates that we're interested in. Given specification for an implication gate, I don't know if you may not know that there was an implication gate, but there is. There is an implication truth table. And an implication truth table is the table that answers the question, if A and not B, then out equals 0. Otherwise, out equals 1. That is, if A is 1 and B is 0, then out equals 0. Otherwise, out equals 1. Notice here, the only time that out equals 0 is when A is 1 and B is 0. Every other case, out is 1, and that is the truth table for implication. Implication is an if-then statement, and this truth table sometimes can be kind of confusing to individuals because it seems at first glance to be a little counterintuitive. Here you have, if A is false and B is false, then A implies B is true. And that just boggles the mind for most people. If A is false and B is false, then A is true. Then out is true. Also, if A is false and B is true, out is true. And obviously, if A is true and B is true, then out is true. Then that makes sense. But this is the only time in implication that out is false. If A is true and B is false. In other words, someone says, this thing that I say is true implies this thing over here that really is not true. Well, if a truth statement cannot imply something that's false. A true statement, if a true statement implies anything, it implies something that's true. If a true statement implies anything, it implies things that are true. So only true statements can imply, well, I'll take that back. Only true statements can be implied. Only true statements can be implied by true statements and by false statements. True statements can be implied by true statements and by false statements. That's what this line says. A false statement can imply a true statement. That makes a true statement. Now, what we're talking about is something called material implication. We're not talking about cause and effect or anything of that nature. We're just talking about material implication, where we're only concerned about the truth of the components or truth of the inputs. And this ends up being the output of implication. It's really kind of confusing, but if you'll, at least for this, for the purpose of this video and for our tests, just assume that this is correct. And this is the output of an implication gate. From the truth statement, we can see three conditions that result in a true out value. 0, 0 is 1, 0, 1 is 1, and 1 and 1 is 1. And the way to build a statement that will specify all of these is by looking at each one of these lines where the output is 1 and build a statement like this that indicates that. Not A and not B implies 1 in this truth statement. And not A and B, 0 and 1, implies 1. And A and B implies 1. And then if we take these three statements and combine them with an OR statement, an OR operator, we can create a truth statement that accurately describes a table. And here is the truth statement that we get by combining these three statements for each one of the lines where the output is 1. Not A and B, or not A and B, or A and B. So we got not A and not B, or not A and B, or A and B. And from this, for what we've done here, we can see that every truth table can be represented using only three logical operators, not, and or. With those three operators, every truth table can be described. And that's pretty amazing when you think that there are literally an infinite number of truth tables out there of varying complexity. Truth tables with 2 inputs and 1 output, truth tables with 4 inputs and 2 outputs. All those truth tables can be described with these three operators, not, and or. And that's going to be important to us as we go along. Now, here's that statement again. If we notice that in these first two parenthetical statements, then not A and not B, and this parenthetical statement, not A and B, these are identical except for the sign of B, not B and B. And from that, we can deduce that this just boils down to saying not A. So we can take this whole statement and say either not A or A and B. And that not A or A and B describes this truth table. So we've simplified this truth statement to not A or A and B. If A is, in other words, if A is false or both A and B are true, then the output is 1. And then from here, we can build the gate. An implication can be implemented with the 3 gates: a gate for not, a gate for or, and a gate for and. And so we come down here, we've got a not gate, we've got an and gate for and A and B, and we've got an or gate for not A and A and B. Goes through the or gate, and that gives us the out gate. And so implication here can be implemented with these 3 gates, and that is how you would, one of the ways that you would figure out the design that you need in order to build the implication gate. In HDL, the language that we're using, if we have this logic, not A or A and B, this is how we would implement it in HDL. We have a chip. We have the chip that we call implies. The gate is called implies. It has two inputs, A and B. It has 1 output, out. It has 3 parts. We've got a not part, an or part, and an and part, and we put them together by just tying the parts together. Now this is a little bit confusing until you get the hang of it, but let's see if we can't look at this and explain it so that it makes sense. We have the not operator, and in order to tie up the not operator, which is indicated up here, we want to get the input of the not operator equal to A. And the not operator has an input called A. And we're going to set it to be equal to A. I'm thinking maybe the not operator has an input called N. And so that's that would be the case. Not operator is going to have an input here called N. So IN equals A is what that should be. And this is the not, a not pin. The left side of the equals statements over here always refers to a pin on the gate that precedes the parenthetical statement here. And so the N pin for not is connected to the A input for the implies gate. These are the inputs, A and B. And the out pin for not is going to go to a wire, and the wires are named, and we try to give the name to the wires that indicate what that wire is and where it is in the circuit. So we've got a wire here called not A, and so the output for not is going to go to the not A wire. And then we have the AND input, or the AND gate. And the AND wants to get its inputs from A and B. So the AND A is connected to A from the input of the implies. The B input for AND is connected to the B input for the implies. And the output for AND is connected to the A and B wire, the A and B wire that we've created right here in our circuit. And then finally, for the OR gate, we have the A input for OR and the B input for OR here. The A input for OR is connected to the not A wire. So now the not A is coming into the A gate. Notice we always put the gates in the gates pin to the left of the equal statement, and then we get a wire or an output to the an output for the chip that we're building would be on the right. So it's either going to be a wire here on the right, like like not A and A and B, or it's going to be the output of the chip that we're creating. So that would be the output of the chip implies. So the OR gets its A input from not A, its B input it gets from A and B, this wire, and its output goes to the output of the chip. And we close each one of those lines off with a semicolon and close this section of the chip's logic with a bracket, and that's how you create the HDL file for the implies gate. All right, now let's take a look at some live demonstrations. We'll close down PowerPoint and open up some other tools here. And first of all, let's take a look at the hardware simulator. Hardware simulator comes up, looks like a normal Java application, and it's not much to look at really, but let's load up I'm sorry. Let's load up a project here, find out where I'm at. Okay, here we're on the desktop, and I want to go over to my documents folder, find one of my completed ones. This is the ALU from next week's challenge, but this is a look of the HDL file. It looks like you could move these, make the window a little bit larger, and so on, but really it doesn't help very much to change the size except for down here, because the status bar is hidden if you don't make that window a little bit larger than what it's designed to be. But this is the HDL file I just loaded up, and you can see the internal pins and the value that are set on those pins. Actually, what I called these in the before were the wires, the internal wires of the thing, and then this the input pins, the input for the ALU and the output for the ALU, and you'll learn by using this how to go in and test values and so on. You can go in and change these values to whatever value you're interested in. This is a 16-bit value, so it can take a number up to 65,000 or something. And the 1-bit pins obviously can only take a 0 or 1. And then the ALU will take these values and produce an output. I'm going to come over here and load up a script. And the script I'm going to load up is the ALU test. And now we have this script over here. And if I run this ALU test, it will go through and do a number of tests on the ALU to see if it's working correctly. And we have up here a single stepper where we can make it just do one step at a time, or we can tell it to run the entire script. Let's do a single step. And the first thing it did was to load the ALU.hdl file. And the reason it loads it at the beginning of the script is because you may have made changes to the HDL file since the last time you loaded it up. And the idea is you can run a test and see what's wrong, make a correction in the HDL file, then start the script again, and it will automatically load it up. You don't have to go through that part of the process by yourself. We'll run another step. So we've set X and Y, and we're going to set some other values and evaluate them. And we keep doing that for the whole file. Let me just run the whole thing now. Let it complete. And it goes on and runs through this test script. And you can see the values changing here based upon the inputs that it's giving to the chip. And if everything goes well, it will come to the end and give us the result. So we now get to the end of the script, and it says comparison ended successfully. And now we know that that the ALU, at least as far as this test script is concerned, is designed correctly, and it's ready and able to do the work that it's designed to do. Let me give you a look at the tool that I'm working on for this project. This is going to be in, let's see, it's going to be in my source files. Under debug, and it's called head. And this is designed to make it a little bit easier to write those test scripts. Instead of having to do everything in a text file, you'll be able to do it within a table. And these tabs here specify different parts of the HDL file that you'll be editing. These are the input pins for the gates, the output pins, the parts that you specify for the gates. This will have a list of parts on it and give you the connection and description. On the right-hand side is where you can edit the connections for the part that you have selected over here on the left. Then the header text at the very top of the HDL file, the API text, and description text that goes beneath the HDL file, and then a file view that will show you what the file will look like when it's saved and loaded up into a text editor. You can go in and we can go in and open up an HDL file. We'll just take a look at the ALU file again here. And now that we've loaded it up, we've got the gate name here that it got out of the file. We have all of the input pins for the gate. We have the output pins listed. And now we have a parts list, everything that goes in there, plus the connections. The connections are kind of long on some of these, so that I'm sorry, pardon me. We make that a little bit smaller. And then the descriptions over here on the right. If you connect, if you select one of the lines here, then the connections that connect to the wires and to the outputs are going to be over here. So we have the part pin, the pin that goes to that here that you're specifying, the MUX16, each one of the part pins and how it's connected to the external pin over here on the right. The header text, the API text, the description text, and here's the file view for the ALU. And in the settings menu, there is a place you can come in and specify where you want your files to be saved. You can specify the components factory. This is the components factory is a folder, is the location for all the folders that will be available to you during your designing process. And so if you point that to a folder that has a MUX gate in it, for example, then the idea is you'll have that MUX gate available to you. You just don't have to memorize the name of it, but you'll be able to pull it out of a drop-down list for the application. And you can print off the file and so on. So basically, most of this is going to be pretty well self-explanatory. One difference is you're going to have a default save directory, and it can be anything you want it to be, but you have to define it here under the settings. And then over here on the right, there's a button that you can press to save that HDL file, and the HDL file is going to be named based upon the gate name ALU with a .hdl. And the reason that we do that is because some of the simulators, the simulator that we're going to use depends upon the name of the file in order to find it for use within its logic. And so we're just going to do it this way, and there's not you don't have a save as option over here to give it some other name. If you want to save it as something else, you can go and change it later with Windows Explorer or something like that. But for the purposes of what we're going to be doing, it needs to be saved based upon the name of the gate with an HDL extension. And that's the HDL editor. I've got a little more work to do on this before it's ready. It just really would not, I don't think you'd be able to do anything with it very much right now. For example, I don't have a way to add a line in this in this list, so I can't add any more pins, input pins, and I can't add any more output pins in here. I can edit them, but I can't add anything. I can't delete anything without just clearing the whole thing. So a little more work to do on that, and hope that when I'm finished, it'll be something that will help users out. So I think that's just about it for today's lesson. How about let's go and take a look at the I'd like to take a look at the information on NAND to Tetris, where we're going to look at the projects. This is, you can go here and get information about the projects. This is the one we're doing today, Boolean logic. And this is some information about the tools. You can get some information about these gates that you want to create, and some more information about this, and you'll get a better understanding of what's going on. Here is a section out of the book that the authors of the Coursera class wrote, called The Elements of Computing Systems, and this is chapter 1, the Boolean logic, and that's available to you if you want to download that and read it. And I'm not sure what this is. Oh, this is a PowerPoint presentation on Boolean logic, if you want to look at that. Software that you want to download is here. Download it from this link right here, and so on. And a lot of other stuff in here that you may be interested in, and some Q&A stuff and so on that will help you out. So go over there and find out what you can about that. Well, I hope that this has been